You've just spent the last 3 weeks staring at Gazebo. You've tweaked the PID gains, dialed in the swing trajectories, and finally, your quadruped is executing a walking gait on your screen. Then you deploy that exact same code to your physical hardware. You power on the servos and step back. Immediately, the physical robot twitches, loses its delicate balance, and collapses into a heap on the hard lab floor. Your first instinct is usually to blame the controller. You go back to your desk, assume your tuning was slightly off, and start adjusting your math to account for the physical hardware. If the simulation allows for physical shortcuts that don't exist in reality, a controller that looks perfect on screen is doomed to fail. To solve this, we have to look at how the virtual physics engine approximates the physical world. To find the discrepancy, we look at the simulation loop. Every single millisecond, Gazebo runs a sequence of events to approximate how your robot interacts with its environment. This diagram outlines that pipeline. Your controller math feeds servo commands into the physics engine. The engine calculates the forces and constraints, and it outputs the simulated gait. Relying on forgiving default settings trains your controller to exploit mathematical loopholes. It learns to walk in a universe with soft floors and inconsistent contact forces, loopholes that vanish the moment you hit the power switch on real hardware. To narrow this gap, we need to evaluate how the three main physics engines, ODE, Bullet, and Dart, mathematically handle a 12-joint quadruped. We'll start with the Open Dynamics Engine, or ODE. This is the default option in many setups because it's fast and computationally cheap. ODE gets its speed by using a quick project solver. Instead of finding a precise mathematical answer for how hard a robot's foot hits the floor, it uses an iterative method. It guesses the force, checks if the leg is clipping through the ground, and refines the guess a few times until it's close enough. Because a quadruped has 4 legs, guessing the force for leg 1 alters the geometry for leg 2. Adjusting leg 2 affects leg 3. By the time it calculates leg 4, the errors have compounded. This compounding mathematical error creates a specific physical symptom. If you've seen your real robot twitch or oscillate at 2 Hz, you're watching the ODE iterative loop failing to maintain a stable stance. ODE is effective for fast simulations of simple, rigid bodies, but for the precise contact requirements of a quadruped, the compounding errors make it a poor choice for simulation accuracy. That brings us to Bullet physics. It uses a constraint-based matrix solver instead of iterative guessing. Looking at our contact points again, Bullet solves all 4 ground constraints simultaneously. There is no guessing loop, so the compounding errors disappear. Bullet has a drawback for robotics, however. It treats your quadruped as 12 independent bodies, forcing them together as constraints after the physics are calculated. While Bullet handles soft bodies and general physics interactions well, treating a complex 12-degree-of-freedom robot as a series of post-hoc fixes is suboptimal for articulated systems. This leaves Dart. Unlike the others, Dart is a specialist engine designed specifically for articulated robots and humanoids. Dart utilizes Featherstone's algorithm to treat the entire 12-degree-of-freedom quadruped as one unified kinematic chain. It computes the forward dynamics pulling down from your servo torques and the backward constraint forces pushing up from the floor at the same time. The practical result is coordination. If the front left leg pushes into the floor, the mathematical model immediately informs the back right leg. The articulation is baked into the math from the start. This integrated approach allows virtual gaits to transfer much more predictably to physical hardware. Even with Dart, the simulation is only as accurate as its underlying time step. If this parameter is set incorrectly, your gait will still fail. This graph illustrates the time step trap. If you set your step size to 10 milliseconds, the engine undersamples the moment the foot hits the floor. It literally misses the precise point of impact. Because the physics engine only detects the floor after the foot has already penetrated it, it tries to undo the error by applying a massive corrective impulse. This causes a violent vertical bouncing effect that ruins stance stability. Conversely, a 10 kHz time step provides excessive detail that grinds reinforcement learning pipelines to a halt with zero hardware benefit, as most servos only respond at 50 Hz. A 1 millisecond step size, or 1 kilohertz, allows you to capture contact forces 20 times finer than the actual leg movement without wasting computational power. Accuracy also depends on avoiding forgiving physics settings, specifically constraint force mixing, or CFM. Any value above 0 creates a soft physical boundary. Soft constraints allow the foot to intersect the floor mesh. Over a 30-second walk cycle, this creates an unexplained drift where the robot slowly sinks. The other common simulation cheat involves gravity. If you accidentally mismatch the simulated mass of your robot or reduce the virtual gravity, you are training the controller for a lighter world. In a low-gravity simulation, your servos don't have to fight to hold the leg horizontal. The controller never learns to compensate for the actual weight of hardware. These shortcuts ensure that when you place the robot on real ground, the legs will sag and buckle under the actual weight of the machine. To build a robust controller, you must strip away these forgiving parameters and force the simulation to mirror the physical lab. Use these Gazebo SDF settings. First, set your physics engine to Dart. Second, lock maximum step size to 0.001 seconds. Third, set soft CFM to 0.0, ensuring unyielding contacts. Finally, perfectly match virtual mass to hardware and set gravity to -9.81. This configuration stops the controller from finding shortcuts and forces it to learn real-world stability. If you are optimizing for reinforcement learning, you might find Dart's slower processing speed frustrating compared to ODE. However, time spent in simulation is an investment. Sacrificing simulation speed is the only way to protect your expensive servos from catastrophic failure upon deployment. Once your gate is stable in Dart, you can finally move the controller onto the actual laboratory hardware. You should expect about 85 to 90% behavioral accuracy. Even with a specialist engine, a simulation is still an approximation. Inevitable factors like real-world sensor noise and hardware variance mean you will still need minor manual PID tuning once the robot is on the floor. But by strictly configuring Dart and eliminating the physics engine as a hidden variable, you make the sim-to-real gap manageable and your robot's behavior predictable.